is Robert Panko. I'm a junior, and this is my first year on the RE Autonomous team. I have 3 years of experience in building and flying RC aircraft, and I've been on the hardware team this past year. I'm a safety pilot for competition.
My name is David Tian. I'm a freshman, and this is my first year on the team. As a computer science major, I have studied Java and Python and helped write scripts for the Sense Detect and Avoid team. I've also had previous experience with Arduino and RC systems because of my past interest in electronics. In addition, I helped set up the competition plane and set up its moving parts. As the hardware manager on the team, I will be responsible for making sure that all mechanical and electrical systems are in proper working order and fixing any issues when necessary.
Hi, my name is Dylan Herman, and I'm a junior. This is my 3rd year on the team and first as captain. My first year I worked on the Autonomous Image Processing subteam. I worked with Open Computer Vision, OpenCV, writing software to detect and classify objects and their characteristics. My 2nd year, I led the software development team and worked closely with the group that developed the ground imaging server and software for the onboard camera. This year, while being team captain, I continue to advise the imaging server team and development of the new onboard imaging software. In addition to the above, my experience with UAS technologies consists of the following. I have worked with the Pixar Autopilot system and the MAVLink protocol. As team captain, my responsibilities in the flight line will consist of supervising and assisting as necessary.
Hi, my name is Sean, and this is my first year working on the team as a freshman at Rutgers. From my experiences working at a hobby shop, I was able to gain the knowledge in building and flying RC planes. With the knowledge, I was able to help the hardware developer team to develop the wiring and aircraft's hardware and tuning of the autopilot system. I also have some programming experiences in C and Java, thus I took interest in working on Sense Detect and Avoid. On a competition team, I will be serving as the lead autopilot ground control station manager, and my responsibility will include to maintain a steady communication with the safety pilot and monitoring the integrity of the autopilot systems.
My name is Ethan. I'm a sophomore, and this is my 2nd year on the team. I have no experience with UAS technologies other than what I learned while on the team. Over the past 2 years, I helped develop the software system that our team will be using at the competition. I focused on the web development and networking portions of our software system. My role on the flight line will be lead image viewer. I will review the images captured by our plane's camera and classify objects. In addition, I will be in charge of monitoring the imaging system on the flight line and repairing any errors in real time.
My name is Ryan. I'm a senior, and this is my 2nd year on the team. I have UAS experience due to my personal interest in quadcopters and RC planes. During the development phase, I worked on the UAS hardware, constructing the plane and setting up the electronics. On the flight line, I will be the lead hardware manager, making sure that all electronics are set up and that the plane is mechanically ready to fly. I will also hand launch the plane.
My name is June. I'm a sophomore, and this is my 2nd year on the team. I have experience in building the plane's hardware and programming for autopilot system. In the team, I worked on programming for Sense Detect and Avoid, and inner server, and simulation testing for autopilots. As the autopilot control station manager, I'll plan out the mission, monitor the status of the plane, and post telemetry to the inner server.
My name is Kendrick. I'm a junior, and this is my first year on the team. My interest in quadcopters led me to this club, where I could utilize my programming and hardware skills from my electrical and computer engineering background. My responsibility on the team for the competition is an image viewer, where I have to set up the imaging server and identify objects from the processed images.
Hi, my name is Jan, and I'm a junior, and this is my first year on the team. My experience with UAS technologies stemmed from working with electronics and programming, from being in the computer engineering major. My position on the team is an image viewer, where my responsibilities is to view images taken from the drone and crop and classify objects. In addition, I will be working on setting up the imaging ground station.
RE Autonomous is using a fixed-wing dual-motor aircraft known as the My Twin Dream for the competition platform. The Pixar Autopilot system is used for autonomous flight and is connected to the ground station with a 900 MHz RFD 900 Plus radio modem. Receiving images from the onboard camera is an Intel NUC computer, which sends them to the ground station using the Ubiquity Bullet M5. An onboard Arduino fetches GPS data from the Pixhawk and sends it to the NUC for geotagging. The ground station is divided into 2 components. The first is the Autopilot Control Station, which consists of mission planner tunneling telemetry and commands through MAV proxy. MAV proxy is connected to the UAS over the RFD 900 Plus modem. The second is the Central Control Station, where the Central Control Server receives and processes images from the UAS over the rocket access point and communicates with the interop server, posting UAS telemetry from MAV proxy and classified objects. In addition, 3 image viewer interfaces are used to view images from the central control server and classify objects in real time. Both stations are linked via router and switch.
We plan to fly completely autonomously. This includes both autonomous takeoff and landing. Takeoff will be performed using a hand launch with autonomous climb out. We expect to fly the entire sequence of waypoints with an accuracy of less than 100 feet and stay within the bounds the entire flight. US telemetry data will be uploaded to the IROP server at approximately 10 Hz. Objects will be detected and classified by 3 human operators. The team will not be attempting autonomous detection and classification of objects. However, all object submissions will be actionable. Localization will be performed by an algorithm running on the ground imaging server. The team will also be attempting to capture the emergent target but will not be attempting to capture the off-axis object. The team will not attempt obstacle avoidance or air delivery. Our expected performance at competition is based on our full mission tests conducted. Our system has gone through many partial mission tests throughout the year, testing different components of the system. We have conducted 4 full mission tests and graded each one based on the rubric provided in the rulebook. Based on these results, we are confident our system is capable of completing all tasks we are attempting, except localization. In all mission tests, localization works but does not provide reliable or consistent results. However, we hope this can be improved with further mission tests. Overall, we believe our system is mature enough and our team is ready to compete.
Now we will explore developmental and individual component tests for the various systems included in the project. The team utilized a bottom-up testing technique for developmental testing that consisted of 3 stages: requirements testing, module/component unit testing, and integration testing. Requirements testing was the first stage and consisted of reviewing the requirements presented by the competition, selecting hardware as candidates for our solution. Typically, the specs for several components were first compared to narrow the list of candidate components, could then be physically tested by the team. One example of a physical test during the requirements stage was to take pictures of targets at varying distances, test the quality of individual cameras. Physical tests then allow the team to select which equipment to use. While hardware and some algorithms went through requirements testing, software components including individual modules of the onboard computer software, the imaging server, and features of the chosen autopilot such as autonomous takeoff and landing were subjected to module/component unit testing. This stage took place during system development and helped identify the presence of bugs in the individual system. Unit testing also revealed design flaws in a module, forcing the team to think the solution or make modifications of the system design. Unit tests for individual modules were successful and would then test the integration of multiple modules. An example of integration tests consisted of triggering the camera from the onboard computer, fetching telemetry information about those images from the autopilot, and then sending the information from the onboard computer to the ground. The process continued until all components were mature enough for a full mission test.
Tuning for autonomous flight first began with Pixhawk's automatic tuning mode. This produced good approximations for the adjustment values, namely PID, for the flight controller. To further enhance flight characteristics, multiple parameters such as the waypoint radius, time periods, and dampening values were adjusted. Flight tuning was conducted with multiple flight tuning missions that tested the vehicles against sharp turns. For configuring autonomous takeoff and landings, appropriate speed, climb, and descent values are first measured based on the aircraft's cruising characteristics. In autonomous mode, these values are further refined after landing and takeoff test runs. After tuning, partial and full mission tests were performed. Most missions lasted about 5 minutes, including 1 or 2 minutes in manual mode. In summary, the longest flight lasted about 37 minutes, including 5 minutes in manual mode. Overall, the team has conducted approximately 40 autonomous flights, where data for 4 are displayed later. Although early autonomous flights are mostly waypoint and search area navigations, tasks were added to the mission as more system components are tested and integrated.
Waypoint accuracy and boundary adherence were tested using the interoperability server provided by the AUVSI-SUAS developer team on GitHub. In addition, for redundancy, waypoint accuracy was tested using a MATLAB program with data from our own telemetry files. During our test flight days, we created waypoint sequences and flight boundaries using Mission Planner and import them into mission configs on the interoperability server. We use the server's built-in mission evaluation feature in conjunction with Mission Planner's logs to score ourselves. Based on our test flights, we expect that we will hit every waypoint within an average of about 50 feet and will stay within the mission boundary for the entire flight. It must be noted that our test flight space is significantly tighter than the competition flight space, which may result in deviations in performance.
For testing the quality of images, the team performed pre-flight tests to calibrate the lens's focal length and aperture.
This ensured that all objects were in focus and that no pictures were overexposed. In addition, an initial analog gain was set for the camera. However, this parameter is configurable from the ground station in real time. Since the images come in at very high speeds, the operator will be able to quickly compensate for necessary changes in exposure. For each crop, the object was more than 25% of the image, and there was enough resolution for an operator to easily identify a target. We also tested two different types of lenses, 30mm and 50mm, to determine the necessary field of view to cover the field in one pass. In addition, we performed tests to determine the required frames per second to ensure enough image overlap. Lastly, given the required field of vision and FPS, we needed to determine the number of human image viewers required to go through all the images before the aircraft landed to ensure actionable submission. It was found that a 30mm lens on a camera taking pictures at 2 to 3 FPS and at least 3 human operators was sufficient.
Detection is handled by utilizing Open Computer Vision Library known as OpenCV. OpenCV has several feature-based detection algorithms which would be utilized for detection. Testing was done by using images taken from fly days and running them through the system. Images varied from different lighting, number of targets, and even different weather conditions. By having varied test set, we can determine the general performance of the algorithm being tested. The result shows us that maximally stable extremal regions, also known as MSER, perform the best due to its ability to detect targets through varied light situations. In the images shown, Canny Edge Detect, on the left, detects a lot of noise in comparison to MSER. The table shown here shows how well MSER performed through the test set, which contains either no object, a single object, or multiple objects.
The team developed a shape classification system that utilized support vector machines. Testing was done using cross-validation sets to look for overfitting. The classifier was trained and tested on simulated objects as well as actual ones. While the algorithm performed well on its test set and other simulated objects, it was not able to classify extracted objects from real images correctly, so the generalization error was high. The team adjusted the training set size, but the error did not change. To attempt to mitigate this, the team decided to look into other features for classification, but ran out of time. Testing was also done on the color classification and character extraction algorithms, which showed they were successful on real objects. However, since the shape classification and OCR system were unable to be completed, and since there was no partial credit for autonomously detecting objects or classifying certain characteristics of objects, the team decided not to integrate the software for detection and classification that were completed into our system, so classification and detection will be performed by at least 3 human operators.
Localization was determined by using the PixSOT data, then running it through a script to determine the object's coordinates. Testing was done by taking the actual GPS coordinates of each target via a cell phone's GPS, then comparing the data over with the results of the script. From this, the percentage of average localization error was then determined.
The heading of each target is determined by first finding the heading of the aircraft obtained from telemetry at the time the picture of the target was taken. The orientation of each target is determined by finding the angle offset between the orientation of the image and the vertical axis of the recognized character. Using these two measurements, the ground station is able to determine the overall heading of the target.
We conducted 4 full mission tests and graded each one based on the rubric provided in the rulebook. For each mission test, we set up our plane and ground station at the field, uploaded a mission to a computer running the interoperability server, laid down alphanumeric target objects, and ran the mission. Each mission was conducted with different wind and cloud conditions, different alphanumeric objects, and different search areas in the waypoint navigation paths, which allows us to be confident in a variety of potential conditions at competition. You can see summaries of our performances in the chart here. We scored 24% on our first mission, 28% on our second mission, 46% on our third mission, and 55% on our fourth mission. Our average score was 38%, but note that our grade improved over time, so we expect that our fourth mission will be the most indicative of our performance at the competition. The high subscores from the fourth mission show that our system is capable of completing the planned tasks under the timeline, autonomous flight, and object detection and classification sections. Also, the scoring data from our early missions helped us expose flaws in our system. As you can see, we were originally doing poorly on the autonomous flight section, which was because we had too many manual takeovers, and doing poorly on the object detection, classification, and localization sections because our system was originally incapable of processing images fast enough for the object submissions to be actionable. We were able to correct these flaws by the fourth mission. Note that even in the fourth mission, we still only received a 58% in the object detection, classification, and localization section, because we did poorly on localization and did not achieve object autonomy. However, we will continue to improve our performance over the next month until competition.